A developer downloads a 13 billion parameter model on a Tuesday afternoon. The download completes, the model loads. The first inference takes 47 seconds. The second takes 41. By the third, the developer has already decided this is not going to work. The model goes in the trash. 2 weeks later, a colleague runs the same model on the same machine after applying a 4-bit quantization. First inference takes 3 seconds. The model is now in production, handling internal document queries for a team of 12. The hardware did not change. The understanding of what the hardware required did. This is, can your hardware run this model? Models Part 3. The answer is probably yes. The answer to how well depends on what you're willing to spend. Section 1. Memory runs this, not processing speed. Most guides to running local language models lead with the model. Download this, run that, see what happens. The hardware discussion arrives later, usually after something fails. This arc does it in the other order. Hardware determines which models are viable, which serving configurations are practical, and what your per inference cost looks like before you commit to a stack. Getting this wrong early means rebuilding decisions that should have been made once. The good news is that the minimum viable hardware threshold drops significantly between 2023 and 2026. The bad news is that can run it and can run it well enough for production are still different answers for most consumer setups. Section 2. What a model actually consumes. Language models are memory problems before they are compute problems. The limiting resource in almost every local deployment is not processing speed. It is how much memory your system can hold the model in while serving inference requests. A 7 billion parameter model in 16-bit precision requires approximately 14 gigabytes of memory load. The same model quantized to a 4-bit precision requires approximately 4 gigabytes. Quantization requires memory requirements by representing model weights at lower numerical precision. The capability penalty for 4-bit quantization on a well-quantized model is measurable in benchmarks and difficult to detect in most production use cases. This is why the developer in the opening scenario got 3-second inference after quantization. The model stopped fighting the hardware and started using it. Section 3. The hardware tiers. There are 4 practical tiers for running a language model in 2026. Each tier has a ceiling on what it can run comfortably and a floor below which inference becomes too slow for production use. First, a consumer GPU in the 8 to 12 gigabyte VRAM range on an NVIDIA RTX 3060 or 3070 is the minimum viable tier for a 7 billion parameter quantized model. Inference at this tier runs comfortably for a single user or low concurrency workloads. A team of 1 to 5 users querying an internal tool will not saturate this hardware. A team of 50 will. The RTX 3060 with 12 gigabytes of VRAM is the lowest practical entry point for the build in this arc and costs under $500 on the used market in 2026. Second, a mid-range consumer GPU in the 16 to 24 gigabyte VRAM range, an RTX 3090 or 4090, handles 13 billion parameter models comfortably and 7 billion parameter models at high concurrency. This is the tier where most serious hobbyists and small team deployments live. The RTX 3090 with 24 gigabytes of VRAM runs the full build in this arc without constraint. Used market prices sit between $800 and $1,200. Third, Apple Silicon from the M2 generation forward is a legitimate alternate to the discrete GPU deployment. The unified memory architecture means that a Mac Studio with 64 gigabytes of unified memory can load and serve models that would require a multi-GPU setup on a traditional PC. Inference speed per token is slower than comparable discrete GPU, but the memory ceiling is higher and the power consumption is dramatically lower. For a always-on local deployment where inference latency is acceptable at 2 or 4 seconds per response, Apple Silicon is a practical and power-efficient choice. Fourth, cloud GPU instances are the answer when you need to move fast before committing to hardware. An A10G instance on AWS or comparable offering on GCP or Azure gives you 24 gigabytes of GPU memory on demand. Hourly costs for inference class GPU instances run between $1 and $3 per hour in 2026, depending on provider and commitment level. For prototyping the build in this ARC, a cloud instance lets you validate every layer before deciding whether to invest in local hardware. Section 4. CPU inference is slow, not dead. A modern CPU with sufficient RAM can run quantized models using Llama CCP, the inference framework that makes CPU deployment practical. Inference is slow. A 7 billion parameter model on a CPU produces tokens at 2 to 5 tokens per second, compared to 30 to 80 tokens per second on a mid-range GPU. For batch processing workloads where latency is not the constraint, CPU inference is a legitimate option. For interactive use cases, it is not. If your only available hardware is a CPU machine with 32 gigabytes of system RAM, you can follow this ARC. You will wait longer at each step. The output will be identical. Section 5. What this costs to run. Hardware purchase is a one-time cost. Inference is an ongoing one. A local GPU deployment running continuously consumes between 150 and 350 watts, depending on the card and utilization level. At an average of U.S. commercial electricity rates, that translates to roughly $15 to $30 per month in power costs for a continuously running inference server. At low utilization, the cost is lower. At high concurrency, it approaches the upper bound. Cloud inference costs scale with usage. A team making 500 inference calls per day on a shared cloud GPU instance will spend between $50 and $150 per month, depending on instance type and provider. At 10,000 calls per day, the economics shift towards dedicated hardware. The crossover point where local hardware becomes cheaper than cloud inference is typically between 3 and 6 months of equivalent cloud spend for a mid-range GPU purchase. For a production deployment expected to run for more than a year, local hardware wins on cost. For a pilot or proof of concept, cloud wins on flexibility. Section 6. What this ARC needs from your machine. The NOAA Storm event pipeline we build across this ARC will run comfortably on any hardware at or above the minimum viable tier. A quantized 7 billion parameter model on an RTX 3060 12 gigabyte handles every step. An Apple Silicon Mac with 32 gigabytes of unified memory handles every step. A Cloud A10G instance handles every step. Where you will feel the hardware ceiling is in the fine-tuning articles. Training, even with QLoRa, which reduces memory requirements substantially, needs more headroom than inference alone. We address that specifically when we get there. For now, if you have the minimum viable hardware, you have enough to start. Next, the stack itself. 7 layers, each with a specific job, each depending on the layers beneath it. Before you configure anything, you need to know what you are actually building and in what order the pieces go together.